The darkness between stars holds secrets that arrive without warning. On a night in early October 2025, two scientists in Russia stared at calculations that refused to make sense. The numbers repeated. The pattern held. And what they discovered about 3I Atlas, our third confirmed visitor from beyond the solar system, would force astronomers worldwide to reconsider everything they thought they understood about objects drifting through the cosmic void. This wasn't just unusual behavior. This was precision, mathematical rhythm, a cadence so regular it seemed to mock the chaos that governs most celestial wanderers. The announcement came swiftly and unexpectedly through astronomers' telegram 17437. Yuri Medvedev and Sergei Pavlov, working from observatories scattered across Russian territory, had identified something that shouldn't exist in nature. 3I Atlas was shifting its position in a predictable cycle, approximately every 4 hours, with margins of error so narrow they suggested either extraordinary coincidence or something far more deliberate. Simultaneously, its brightness pulsed with even tighter precision, flaring and dimming roughly every 2 hours like a lighthouse beam sweeping across interstellar distances. What makes this discovery seismic isn't just the regularity itself, it's the silence that surrounded it from every other direction. NASA, normally first to announce findings about interstellar visitors, said nothing. The Chinese National Space Administration, with its vast network of observatories, remained quiet. The United Arab Emirates space program, ambitious and vocal about its astronomical discoveries, offered no comment. Even European agencies, typically transparent about their observations, withheld data. Russia spoke alone into a vacuum of institutional silence, publishing findings that other nations either couldn't confirm or chose not to acknowledge. This isn't how space science typically operates. Discoveries of this magnitude usually trigger immediate international collaboration, cross-verification, competing papers racing to confirm or refute the claims. But 3I Atlas has become something different, something that makes agencies pause before speaking, something that sits at the uncomfortable boundary between what we can explain and what we're not yet ready to confront. The Russian announcement wasn't just sharing data, it was breaking a silence that might have been coordinated, intentional, protective of conclusions others weren't prepared to release. Let your breathing slow as we explore this mystery together, piece by careful piece. No sudden revelations, no jarring conclusions, just the steady accumulation of observations that don't quite fit the patterns we've learned to expect from frozen chunks of ice and rock that wander between the stars. By the time dawn touches your window, you'll understand why some scientists are quietly excited and others deeply unsettled by what 3I Atlas is showing us. You'll understand why precision in the cosmos can be more disturbing than chaos. The technical term for what Medvedev and Pavlov measured is OC residuals, which stands for observed minus calculated. When tracking any object through space, astronomers predict where it should appear based on gravity, velocity, and trajectory mathematics that Newton gave us centuries ago. Then they observe where it actually appears. The difference between prediction and reality tells you whether something else is influencing the object's path. For most comets, these residuals are noise, random deviations caused by asymmetric gas jets erupting from sun-warmed ice, by uneven mass distribution, by all the messy irregularities that natural objects accumulate over billions of years drifting through space. 3I Atlas's residuals aren't noise. They're signal, pure, undiluted signal that repeats with a period centered around 4 hours. When you plot these deviations over time, they don't scatter randomly across your graph. They form waves, regular oscillations that suggest something is nudging this comet's trajectory in predictable ways. Natural processes don't maintain such consistency. Natural outgassing sputters and varies as different surface regions rotate into sunlight, as ice reserves deplete, as structural weaknesses develop and collapse. Yet here we have an interstellar visitor maintaining positional shifts that could serve as a cosmic metronome if you needed one. The brightness variations compound the strangeness. Most comets brighten and dim as they rotate because their surfaces aren't uniform. One hemisphere might be icier, more reflective. Another might be darker, coated in organic compounds, baked by eons of cosmic ray bombardment. As the comet spins, we see different faces, and brightness changes accordingly. But these changes are typically irregular, or if there is periodicity, it's loose, approximate, the kind of rhythm you might tap out with your fingers while thinking about something else. 3I Atlas pulses with the discipline of a drum machine, every 2 hours almost exactly, deviating only within narrow margins that make the regularity more striking rather than less. What tool did the Russian researchers use to extract these periods from data that wasn't collected continuously, that had gaps where telescopes pointed elsewhere, or weather intervened, or daylight made observations impossible? They employed something called a Lomskargel periodogram, a mathematical technique that excels at finding hidden rhythms in irregularly sampled data. It's the same method astronomers use to detect exoplanets from the subtle wobbles they induce in their parent stars. It's sophisticated, robust, designed specifically to distinguish genuine periodic signals from the artifacts that irregular observation schedules can create. When Lomskargel analysis returns strong peaks at specific periods, you pay attention, because false positives are rare if you're using the tool correctly. Here's where the mathematical relationship becomes impossible to dismiss casually. The brightness pulse occurs at almost exactly half the period of the positional shift. 4 hours for position, 2 hours for brightness. That's a 2.1 harmonic ratio. the kind of simple mathematical relationship that appears constantly in engineered systems, but rarely in natural chaos. Musical instruments produce harmonics when strings vibrate at integer, multiples of fundamental frequencies. Orbital resonances create harmonics when planets lock into gravitational relationships where their periods relate as small whole numbers. But those are systems that have had time to settle, to find stable configurations through repeated interactions over millions or billions of years. 3I Atlas is a visitor, not a permanent resident. It hasn't had time to settle into resonance with anything in our solar system. It arrived from interstellar space, already spinning with this precise harmonic relationship between its rotation and whatever mechanism creates the brightness variations. That strongly suggests the relationship isn't coincidental, isn't something that emerged from random initial conditions. It suggests either an extraordinarily improbable natural formation process or something that was balanced deliberately, designed to exhibit exactly these mathematical properties that would make observers like us notice and wonder and question whether we're seeing nature or artifice. The Russian announcement didn't speculate about artificial origins. It simply presented the data, the periods, the statistical significance of the Lom-Skargel peaks. Scientific papers maintain carefully neutral language when dealing with observations that might imply extraordinary conclusions. But the implications hover around every precisely measured number, every confidence interval, every description of how unexpectedly regular these patterns appear. When Medvedev and Pavlov wrote that the periodicity was detected with high significance, they were speaking in the understated language of professional astronomy. What they meant, translated to plain speech, was, this is real, this is repeatable, and this doesn't match anything we've seen before in objects that should be natural. So tonight, as you settle into rest, consider what regularity means in a universe that trends toward disorder. Consider what it takes for an object that's traveled light years through the galaxy to arrive at our solar system spinning like a precisely calibrated instrument. Consider why multiple space agencies might choose silence when faced with data that suggests such precision. Because silence in the realm of space exploration is rarely empty. It's usually filled with people arguing behind closed doors about what can be said, what should be withheld, what the public needs to know versus what might cause unnecessary alarm or premature speculation. Russia's decision to publish represents more than scientific transparency. It's a strategic move in the subtle competition that exists among spacefaring nations, the race to be first, with discoveries that might reshape humanity's understanding of its cosmic context. When you're the country that announces a finding of this potential magnitude, you cement your place in history regardless of how the interpretation ultimately resolves. If 3I Atlas proves to be something extraordinary, Russia will forever be remembered as the nation that recognized it first, that had the courage or recklessness to speak when others remained silent. But strategic considerations aside, the data itself demands attention. The 4-hour positional shift, more precisely stated as 4 hours plus or minus 2 hours, means the true period could range from 2 to 6 hours. That's substantial uncertainty, the kind that makes cautious scientists hedge their conclusions. Yet even with that uncertainty, the signal persists strongly enough to register as statistically significant in the Lomskargel analysis. The brightness pulse at 2 hours, with uncertainty of approximately 1.33 hours, similarly shows enough consistency to rise above noise. These aren't tentative whispers in static. They're detectable patterns that multiple observation sessions have confirmed. The coordination required to observe an interstellar comet systematically is more complex than it might seem. Telescopes scattered across Russia's vast territory allow coverage as Earth rotates, ensuring that 3I Atlas remains visible from at least one observatory, even as it moves across the sky, and others lose line of sight. This distributed observation network helps reduce gaps in the data, though gaps inevitably remain when weather interferes, or when the comet passes too close to the Sun's position as seen from Earth, making observations impossible during daylight hours or in the solar glare. Each observation session captures the comet's position against background stars, measuring coordinates precise to fractions of an arcsecond. Each session records brightness through standardized filters, quantifying exactly how much light the comet reflects or emits at specific wavelengths. Over weeks and months, these individual measurements accumulate into data sets that reveal patterns invisible in any single observation. You cannot see the 4-hour shift by looking at one night's images. You see it only when you compile weeks of tracking data, plot the deviations from predicted positions, and step back to examine the resulting curves. The pattern emerges like a photograph developing slowly in chemical baths, details clarifying gradually until suddenly the image becomes unmistakable. Other observatories worldwide have been tracking 3I Atlas since its discovery in July 2025, though not all have published their findings. This is where the institutional silence becomes particularly intriguing. If Russian astronomers detected these periodicities, what are their counterparts in other nations seeing? Are they observing the same patterns and conducting additional verification before going public? Are they seeing something different that contradicts the Russian claims? Or are they seeing exactly what Medvedev and Pavlov reported, but receiving guidance from their funding agencies to delay publication pending further review, further consideration of implications, further consultation with officials who worry about public reaction to observations that might suggest something beyond natural phenomena? The history of interstellar object detection is brief but instructive. When Oumuamua arrived in 2017, the first confirmed visitor from beyond our solar system. It took weeks for the astronomical community to reach consensus on its basic properties. Initial observations suggested it might be a comet, then an asteroid, then something that didn't fit cleanly into either category. Its trajectory showed slight acceleration that couldn't be attributed entirely to gravity, sparking debates that continue today about whether natural outgassing could explain the effect or whether more exotic explanations merit consideration. The discussion was contentious but public, conducted through preprint servers and conference presentations and media interviews that allowed the world to watch scientists grappling with uncertainty in real time. Oumuamua Borisov, the second interstellar visitor detected in 2019, generated less controversy because it behaved more conventionally. It looked like a comet, acted like a comet, followed trajectories that matched comet physics. Its chemistry was slightly unusual, suggesting formation in a planetary system with different composition than our own, but nothing about Borisov challenged fundamental assumptions or demanded exotic explanations. It was proof that interstellar space contains objects similar to those in our own solar system, reassuring in its familiarity even as it came from alien distances. 3I Atlas occupies uncomfortable middle ground between these predecessors. It's not as overtly strange as Oumuamua, which looked like nothing we'd seen before and accelerated mysteriously. But it's not as reassuringly normal as Borisov either. It presents as a comet, complete with coma and spectroscopic signatures of sublimating ice, yet exhibits behaviors that strain the boundaries of what we consider natural variation. The periodic shifting and pulsing, if confirmed beyond doubt, place it in a category that current comet science doesn't quite accommodate. We have no established framework for explaining how an interstellar wanderer maintains such precise rhythms without active control or extraordinarily unlikely initial conditions. The timing of the Russian announcement carries additional significance. October 2025 marked a period of intense observation as 3I Atlas approached its closest pass to Mars, offering spacecraft in Martian orbit unprecedented opportunities to study the comet from vantage points unavailable to Earth-based telescopes. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express both captured images and spectroscopic data during this encounter. NASA's Mars Reconnaissance Orbiter, equipped with the powerful high-rise camera capable of extraordinary resolution, was optimally positioned for observations that could have resolved surface features and structural details invisible from Earth. Yet data release from these Mars-based observations has been notably slow, complicated by the U.S. government shutdown that furloughed thousands of NASA employees on October 3rd, the exact day 3I Atlas made its closest approach to Mars. Coincidence? Perhaps. Budget politics and cosmic timing rarely align intentionally, but the optics are unfortunate at best, suspicious at worst. The most capable observation platform humanity has ever placed in position to study an interstellar object close up happened to have its operations disrupted on the day that mattered most, and weeks later, we're still waiting for comprehensive data release about what those instruments saw. European Space Agency observations are less constrained by American budget politics, yet ESA has also been relatively quiet about detailed findings from the Mars encounter. Preliminary images have appeared showing 3I Atlas as expected, a faint smudge with diffuse coma, but the detailed spectroscopic analyses, the high-resolution imaging, the full data set that could settle questions about composition and structure remain unpublished or at least uncirculated beyond closed scientific circles. This pattern of delayed release, of data existing but not flowing freely to the international research community as would normally occur, adds fuel to speculation that something about 3I Atlas is triggering caution at institutional levels. So we return to the question that should accompany you into sleep tonight. What creates coordination in silence? Individual scientists have no reason to withhold interesting findings. Professional advancement comes from publication, from being first to report new discoveries. But scientists work within institutions, receive funding from governments, operate telescopes that belong to national space agencies. When those institutions decide that particular observations require careful handling, individual researchers often have little choice but to comply. The Russian announcement might represent either a decision by Russia to break from coordinated silence, or simply a different institutional culture that prioritizes rapid publication over cautious vetting. Either way, their willingness to speak, while others remain quiet, makes the silence from elsewhere more conspicuous, more pregnant with implications we're not yet privy to understanding. Let's examine what these measurements actually mean in physical terms, because the specifics reveal why astronomers find them so difficult to dismiss. When we say 3I Atlas shifts position with a 4-hour period, we're describing oscillations in its trajectory. The comet follows a baseline path determined by gravitational influences, the sun's pull primarily, with smaller contributions from planets as it passes through their orbital regions. But superimposed on that smooth gravitational curve are deviations, back and forth variations that repeat cyclically. The comet moves slightly ahead of where pure gravity predicts, then falls slightly behind, then moves ahead again, all in a rhythm that completes roughly every 4 hours. Natural comets can show trajectory variations due to outgassing, when jets of sublimating ice create thrust that pushes the nucleus in unpredictable directions. These jets are controlled by solar heating patterns, which depend on the comet's rotation, its surface properties, the distribution of volatile ices beneath any dusty mantle that might have built up over time. The resulting accelerations are typically erratic, changing as the comet spins and different regions become active or dormant. They might create trajectory deviations, certainly, but those deviations don't repeat with clockwork regularity because the underlying processes are chaotic, subject to feedback loops and structural changes that prevent stable periodicities from emerging. 3I Atlas's positional shifts suggest something different. Either its outgassing is extraordinarily symmetric, with jets positioned and timed so perfectly that they create regular oscillations rather than chaotic perturbations, or the shifts aren't caused by outgassing at all, but by some other mechanism we haven't identified. The symmetric outgassing explanation requires remarkable coincidence, multiple active regions arrayed around the nucleus in precise geometric patterns, all venting at exactly the right moments during the rotation cycle to maintain the 4-hour period. Possible? Barely. Probable? That's where most planetary scientists would pause, considering whether they're invoking too many special conditions to preserve a natural explanation. The brightness variations add crucial context. If the 4-hour positional shift were somehow natural, an accident of fortunate geometry, we might accept it as extraordinary luck. But when that shift correlates with brightness pulses at half the period, when the two periodicities exhibit a perfect 2.1 harmonic relationship, coincidence becomes harder to defend. Harmonics arise in systems where components interact, where one rhythm drives or constrains another. A rotating object with two reflective regions positioned opposite each other would naturally brighten twice per rotation as each region faces the observer. That's a 2.1 harmonic between rotation period and brightness pulse. But such an object would need nearly perfect symmetry, two regions with almost identical reflective properties placed at almost precisely opposite points on the surface. Consider what maintaining such symmetry requires across interstellar journeys. The object would have spent millions of years in the void between stars, bombarded constantly by cosmic rays that alter surface chemistry, pelted by micrometeoroids that crater and erode exposed ice, subjected to temperature swings as it passed through regions of varying radiation density. Natural processes don't preserve symmetry through such conditions. They erode it, introduce irregularities, turn whatever order might have existed into chaos through accumulated insults over geological timescales. Yet 3I Atlas apparently arrived at our solar system with symmetry intact, spinning with harmonic precision that suggests either it was formed very recently or something about its structure resists the randomizing effects that normally dominate. The Lomskargel periodogram analysis provides quantitative measures of how strong these periodic signals appear in the data. When you run Lomskargel on a dataset, it calculates power spectra, showing which periods produce the strongest correlations with observed variations. High power at a specific period means that assuming that period exists explains the data far better than assuming random fluctuations. The Russian team reported high significance for both the 4-hour and 2-hour periods, meaning the statistical tests strongly favor these periodicities being real rather than artifacts of observation scheduling or data analysis choices. But statistics alone don't guarantee physical reality. Science history contains numerous examples of patterns that appeared statistically significant but ultimately proved to be illusions, artifacts of how data was collected or analyzed. The famous face on Mars from Viking orbiter images looked compelling in low-resolution photos, but revealed itself as a hill lit from an unusual angle when higher-resolution images became available. Pulsar signals were briefly considered possible alien beacons until neutron star physics provided natural explanations. Cold fusion experiments produced statistically significant results that couldn't be replicated independently. Skepticism about patterns, even statistically robust ones, is warranted until independent verification confirms the findings using different instruments and analysis methods. That verification is precisely what should be happening now with 3i Atlas. Other observatories worldwide should be analyzing their own data sets, checking whether they see the same 4-hour shifts and 2-hour pulses, publishing confirmations or refutations of the Russian claims. The fact that this verification process is either proceeding silently behind institutional walls or hasn't occurred at all suggests either that other teams are still working on their analyses, or that the results are complicated enough to require careful interpretation before going public, or that institutional guidance is shaping what gets published when. In a perfect world, science operates transparently with rapid sharing of all findings. In reality, science operates within human institutions, subject to political pressures, funding constraints, and concerns about reputation and public reaction. The 4-hour period itself is interesting from an engineering perspective. If you were designing a probe for interstellar travel, you'd want spin stabilization to maintain orientation over thousands or millions of years without requiring active control systems that might fail. Spin stabilization is among the oldest and most reliable spacecraft techniques, used by everything from rifle bullets to deep space missions. A spinning object resists changes to its orientation through conservation of angular momentum. Set it spinning during launch with proper mass distribution, and it maintains that spin essentially indefinitely in the frictionless vacuum of space. 4 hours represents a relatively slow rotation for a small body. Most asteroids and comet nuclei rotate faster, with periods ranging from minutes to tens of hours. Slow rotation offers advantages for an engineered probe. It produces lower centrifugal stresses, allowing lighter construction without risk of structural failure from spin forces. It's easier to observe and measure precisely from distance, not requiring high-speed cameras or rapid sampling to characterize. It provides a rhythm detectable by civilizations that have achieved basic astronomical capability but might not possess more sophisticated detection technologies. If you wanted to create a signal that says, "Notice me," without being too obvious, a multi-hour rotation period with embedded brightness variations would occupy a sweet spot of detectability. The 2-hour brightness pulse could be achieved remarkably simply if the object were engineered. Two reflective surfaces positioned opposite each other on the rotating body would automatically create twice per rotation brightness peaks as each surface sequentially reflects sunlight toward observers. No electronics required. No moving parts beyond the rotation itself. Just passive optical geometry that generates a periodic signal as long as the rotation continues. This is elegant engineering, if it is engineering, the kind of minimalist design that maximizes longevity and reliability by reducing complexity to its absolute minimum. But we must be careful not to let engineering intuition override the requirement for actual evidence. Humans are pattern-seeking creatures who excel at seeing design even in natural randomness. We see faces in clouds, hear words in white noise, detect conspiracies in coincidence. This psychological tendency has evolutionary advantages. Better to see predators that aren't there than to miss real threats. But it also makes us prone to false positives, finding meaning and intention where none exists. The history of astronomy is filled with mistaken attributions, Mars's canals being perhaps the most famous, where observers convinced themselves they saw artificial structures that were actually optical illusions created by limited telescope resolution and expectant brains. So, as you drift toward sleep, hold both possibilities without forcing premature resolution. 3-eye Atlas might be the most perfectly balanced natural object ever observed, a cosmic fluke that will eventually be explained through exotic but natural formation processes we haven't yet imagined. Or it might be something that was balanced on purpose, designed to spin with these exact properties for reasons we can only speculate about. The data supports both interpretations, though it strains the natural explanation in ways that make careful scientists uncomfortable. And discomfort, that intellectual tension between wanting naturalistic explanations and confronting observations that don't quite fit, is often the feeling that precedes genuinely new understanding, the moment when paradigms begin their slow, reluctant shifts toward accommodating realities they previously excluded. Comets, as natural objects, simply don't behave the way 3-eye Atlas appears to be behaving. Let's establish what normal comet physics looks like before we can appreciate how abnormal this visitor seems. Every comet humanity has studied up close confirms their essential messiness. They're aggregations of ice and rock and organic compounds that accreted randomly in the outer reaches of planetary systems billions of years ago. Their surfaces are irregular, pockmarked with impact craters, scarred by jets that blast material into space when subsurface ice finds pathways to vacuum. They tumble rather than rotate cleanly, their spin axes wobbling and precessing in ways that make predicting brightness variations nearly impossible without extensive observation campaigns. Comet Halley, visited by multiple spacecraft in 1986, displayed a nucleus darker than coal, with jets erupting from specific sunlit regions. Its rotation period was roughly 7.4 days, but that period varied slightly with each solar approach as outgassing torques changed the spin rate. Wild 2, encountered by the Stardust mission, showed a surface resembling a battlefield, cratered and fractured and structurally compromised by billions of years of abuse. Its rotation was irregular, its shape lumpy, exactly what you'd expect from an object assembled through random collisions rather than deliberate construction. Most instructive is 67P Churyumov-Gerasimenko, the rubber duck comet, studied intimately by the Rosetta spacecraft for 2 years. Rosetta watched 67P's rotation period change by approximately 20 minutes during the observation period, slowing as asymmetric outgassing acted like countless tiny rocket engines firing randomly across the surface. The comet's bilobed shape created complex gravitational and rotational dynamics that defied simple modeling. Nothing about 67P suggested precision or stability. Everything about it screamed chaos, barely held together by weak gravity and structural cohesion that might fail catastrophically at any moment. Against this background of documented comet behavior, 3 Atlas's apparent stability becomes deeply anomalous. A rotation period that does and change measurably over months of observation, that doesn't wobble or precess in detectable ways, that maintains perfect harmonic relationship with brightness variations, despite all the forces that should randomize such patterns. Either we're witnessing the most extraordinary natural accident in astronomical history, or we're seeing something that differs fundamentally from the comets we've studied previously. The probability mathematics are worth considering carefully. Imagine you're assembling a comet nucleus randomly through billions of low-velocity collisions in a protoplanetary disk. Each collision adds mass in a slightly different location, contributes momentum from a slightly different direction, creates a slightly different density distribution in the growing aggregate. The final object's shape depends on thousands of such random events, each unique, each unpredictable. The chances of this process producing a perfectly balanced sphere are essentially zero. The chances of producing a perfectly balanced dumbbell shape with 2 equal lobes are only slightly better than zero. Even if, through remarkable luck, the formation process produced symmetric geometry, that symmetry wouldn't survive the journey through interstellar space. Cosmic rays constantly alter surface chemistry, preferentially affecting ice exposed to the radiation. Micrometeoroids, particles smaller than sand grains but moving at tens of kilometers per second, sandblast exposed surfaces, eroding high points, filling shallow craters, slowly but inexorably randomizing whatever surface structure existed initially. Temperature cycling, as the object passes through regions of varying radiation density, creates thermal stresses that crack ice, open fissures, allow subsurface volatiles to escape. All these processes work against symmetry, introducing irregularities that accumulate over millions of years into thoroughly randomized structures. Yet here we observe an object that apparently maintained its balance across light years of travel, arriving at our solar system with symmetry intact enough to produce harmonic brightness variations. The odds against this occurring naturally are difficult to calculate precisely because we don't have good models for every process that might affect an interstellar wanderer. But intuitively, the probability feels vanishingly small, the kind of coincidence that makes you check your assumptions and wonder if you're missing some mechanism that preserves symmetry better than random processes should allow. Compare this to Oumuamua's situation. That first interstellar visitor showed signs of tumbling rotation with a period that changed as astronomers refined their measurements, exactly the kind of complex, irregular rotation natural objects develop. It accelerated mysteriously, but even that acceleration was chaotic enough to spawn multiple competing explanations, each requiring exotic assumptions about composition or shape. Nothing about Oumuamua suggested the kind of controlled, stable behavior that 3I Atlas apparently exhibits. Oumuamua looked like what you'd expect from a natural object that had been battered and randomized by eons of cosmic abuse. The chemical composition of 3I Atlas, revealed through spectroscopic observations, adds another layer to this puzzle. James Webb Space Telescope measurements show the coma dominated by carbon dioxide rather than water vapor, which is unusual for comet activity at the distances where 3I Atlas has been observed. Carbon dioxide sublimates at lower temperatures than water ice, becoming active farther from the sun where water remains frozen. But most solar system comets show water as the dominant volatile because water ice is simply more abundant in the regions where comets form. Finding a comet where CO2 vastly exceeds water suggests either it formed under very different conditions than our solar system's comets, or its composition has been modified by processes we don't fully understand. From an engineering perspective, carbon dioxide offers interesting properties. It's an excellent working fluid for certain propulsion or thermal management systems. It stores easily as solid ice, sublimates predictably when heated, can generate thrust if vented through appropriately designed nozzles. If you wanted to build a probe that could make small trajectory corrections using materials that would be interpreted as natural comet outgassing, carbon dioxide would be a smart choice. Observers would see CO2 emissions and assume they're witnessing normal sublimation, not deliberate maneuvering. The camouflage would be nearly perfect unless someone looked carefully at the patterns and timing of the outgassing. But this reasoning demonstrates the danger of working backward from observation to explanation. When you know what you're looking for, you can always construct scenarios that fit the data. The real question is whether those scenarios are more plausible than alternatives, whether they require fewer special assumptions, whether they make testable predictions that observations can verify or falsify. Simply noting that carbon dioxide would be useful for a probe doesn't prove 3I Atlas is a probe. It just means we can imagine purposes for the observed composition if we're willing to entertain artificial hypotheses. The water vapor detection from Swift Observatory's ultraviolet observations compounds the chemical strangeness. 3I Atlas was producing water at substantial rates, even when quite far from the Sun, farther than most comets begin significant water activity. This could indicate an unusually dark surface that absorbs solar radiation efficiently, heating subsurface ice enough to drive sublimation at greater distances than normal. Or it could suggest internal heat sources beyond solar radiation, perhaps radioactive decay of long-lived isotopes, or some other mechanism that keeps the interior warmer than external heating alone would explain. Both explanations are possible naturally, but both require invoking conditions that aren't typical for comets we've studied previously. So tonight, as consciousness fades and sleep approaches, consider how chemistry intersects with behavior. An object with unusual composition showing unusual periodicity isn't just two separate anomalies. They're potentially connected. Two pieces of a puzzle that might fit together if we could see the complete picture. But we're seeing through fog, catching glimpses that suggest shapes without revealing full forms. The data hints at something extraordinary while refusing to confirm it definitively. And that uncertainty, that space between knowing and not knowing, is where the most interesting science happens, where paradigms wait to shift if only the evidence pushes hard enough. The silence from other space agencies takes on particular weight when you understand how astronomical discovery typically functions. Science advances through replication, through independent teams examining the same phenomena with different instruments and reaching consistent conclusions. When a significant finding appears in one data set, standard practice demands verification from multiple sources before the community accepts it as established fact. This verification process usually happens rapidly in the modern era of instant communication and shared data archives. Papers appear on preprint servers within days or weeks of initial detection, triggering responses from other research groups who confirm, refute, or complicate the original claims. 3. Atlas's periodic behavior should have triggered exactly this kind of response. The Russian announcement provided specific periods, detailed methodology, statistical significance measures. Other observatories tracking the comet should have immediately checked their own data, running their own Lomscargel analyses, publishing either confirmations that strengthen the finding or contradictions that suggest measurement artifacts or analysis errors. Yet weeks after the initial announcement, the international response remains muted. A few technical papers have appeared discussing the comet's composition and trajectory, but none directly addressing the periodicity claims with detailed independent analysis. This absence could have innocent explanations. Perhaps other teams are still working through their data, ensuring their analyses are bulletproof before publication. Perhaps they're seeing complicated results that don't cleanly confirm or deny the Russian findings, requiring more observation time to resolve ambiguities. Perhaps institutional review processes, always slower than researchers would prefer, are delaying publication while legal and public relations departments assess how to present potentially controversial findings. All of these are plausible, mundane reasons for delayed verification. Or perhaps other teams are seeing exactly what Medvedev and Pavlov reported, and that confirmation is creating institutional discomfort. If the periodicity is real and robust, if it shows up in datasets from American, European, Asian observatories just as clearly as it appeared in Russian data, then the astronomical community faces a decision about how to interpret behavior that natural comet physics struggles to explain. That decision carries implications extending far beyond this particular object. It touches on questions of how we recognize the potentially artificial, what standards of evidence we require before entertaining such hypotheses seriously, whether our current framework for understanding interstellar visitors needs fundamental revision. The government shutdown that furloughed NASA employees on October 3rd provides convenient cover for delayed data release, but it also raises uncomfortable questions. Budget politics in Washington are perpetually contentious, rarely resolved quickly or cleanly. But the timing of this particular shutdown, coinciding precisely with 3I Atlas's closest Mars approach and optimal observation window, strains coincidence. Congressional budget battles don't usually align so perfectly with astronomical events. When they do, when the bureaucratic chaos happens to occur at the exact moment when important scientific data is being collected, skepticism about mere coincidence seems warranted. Consider the alternative possibility that officials within NASA received preliminary findings about 3I Atlas that triggered concern about public reaction or international implications. Not necessarily findings that proved artificial origin, but findings strange enough to merit careful consideration before release. In such a scenario, a government shutdown, however inconvenient for agency operations, provides useful justification for delaying information flow. We'd love to share the Mars observation data, but our analysis team is furloughed and we can't process the raw images until budget appropriations restore operations. It's plausible, defensible, gives cover for whatever internal discussions might be occurring about how to handle anomalous observations. European Space Agency data adds another dimension to this pattern. ESA operates under different funding structures, less vulnerable to sudden political disruptions than NASA. Yet ESA has also been notably restrained about detailed findings from the ExoMars and Mars Express observations. Preliminary images appeared showing the comet as expected, confirming that the spacecraft successfully captured the target. But the detailed spectroscopic results, the high-resolution analysis, the kind of comprehensive data packages ESA typically releases for significant observations remain either unpublished or distributed only within closed scientific circles, not visible to the broader research community. This parallel reticence from independent agencies suggests either remarkable coincidence, all teams independently deciding their data requires more analysis time before publication, or some level of coordination in information handling. Coordination doesn't necessarily imply conspiracy. It could be as simple as agencies communicating about what they're seeing, recognizing that their observations might be controversial, agreeing informally to proceed carefully with verification before making strong public statements. Science institutions have legitimate reasons to avoid premature announcements that might later require embarrassing retractions, but legitimate caution becomes difficult to distinguish from deliberate information management when the delays extend for weeks without explanation. The Mars observations themselves deserve scrutiny because geometry matters profoundly in understanding brightness variations. From Earth, we observe 3 Atlas from one angle, with the Sun illuminating it in specific ways based on the comet's position relative to us. Phase angles, the angle between Sun, comet, and observer, affect how much reflected light reaches our telescopes. From Mars, the geometry is completely different. The comet appears lit from different angles. Spacecraft see different faces of the coma, and any asymmetries in structure or activity should reveal themselves differently depending on viewing perspective. If 3I Atlas's brightness variations are caused by its rotation presenting different surface features to observers, then Mars-based observations should show timing offsets compared to Earth-based measurements. The 2-hour pulse period should remain constant. Rotation doesn't change based on who's watching. But the phase relationship, which part of the rotation cycle appears brightest, should differ depending on viewing angle. Analyzing data from both Earth and Mars simultaneously could help distinguish between shape-based brightness variations and variations caused by other mechanisms like coherent light reflection from structured surfaces that might not depend as strongly on viewing geometry. The fact that we haven't seen published comparisons between Earth and Mars observations suggests either the comparison hasn't been done yet, which seems unlikely given how straightforward it would be, or the results are complicated enough that researchers are still interpreting them. Complicated results might mean the brightness variations don't behave as expected for natural rotation, don't show the predicted viewing angle dependencies, or exhibit unexpected coherence across different observation platforms. Any of these findings would warrant careful analysis before publication, but they would also be precisely the kind of findings that suggest something genuinely unusual about this object. So, as you prepare for sleep, the question of silence lingers. Why aren't we hearing more? What are the telescopes showing that either isn't being shared or is being shared only within restricted channels? The answer might be mundane. Science proceeding at its normal, deliberate pace, researchers ensuring accuracy before publication, institutions navigating bureaucratic complexities that always slow information flow. Or the answer might be more significant. Observations strange enough to trigger caution, findings that don't fit comfortable categories, data that suggests we're seeing something that requires careful handling, because its implications touch on questions humanity has debated for centuries about whether we're alone, whether intelligence exists elsewhere, whether cosmic visitors arrive not by accident but by design. The broader context of interstellar object detection provides perspective on why 3I Atlas matters so profoundly. Before 2017, humanity had never confirmed a single visitor from beyond our solar system, despite centuries of increasingly sophisticated sky surveys. This absence seemed to suggest either such objects were extraordinarily rare, passing through solar systems only once per many thousands of years, or our detection capabilities simply weren't adequate to recognize them when they appeared. Most astronomers favored the second explanation. Interstellar objects probably passed through regularly, but they moved too quickly, appeared too faint, or resembled solar system objects too closely for us to identify their exotic origins before they departed. Oumuamua changed that calculation dramatically. Its discovery proved that interstellar visitors could be detected, that our survey networks had finally achieved sufficient sensitivity and coverage to catch these fast-moving transients. But it also revealed how easily we might have missed such objects previously. Oumuamua was discovered only as it was leaving, already past its closest solar approach, visible for only a few weeks before it faded beyond detection range. If it had passed through a few years earlier, before Pan-STARRS and other advanced survey telescopes came online, we likely would have missed it entirely, never knowing an interstellar visitor had graced our cosmic neighborhood. 2I Borisov arrived just 2 years later, confirming that interstellar objects aren't once-per-century rarities, but perhaps relatively common, detectable at a rate of several per decade given current survey capabilities. The Legacy Survey of Space and Time, scheduled to begin operations with the Vera Rubin Observatory soon, promises to dramatically increase detection rates. Within years of LSST starting regular operations, astronomers expect to find interstellar visitors monthly or even weekly, building a statistical sample large enough to characterize the population. understand whether most are comet-like or asteroid-like, whether they typically show unusual behaviors or conform to natural expectations. That anticipated flood of detections makes 3I Atlas particularly significant. It's likely our last chance to study an interstellar object with focused attention before the LSST era begins, and we're overwhelmed with targets. Every observation now, every spectrum captured, every brightness measurement recorded contributes to a data set we'll use to evaluate whether this object is representative of interstellar visitors generally or an outlier requiring special explanation. If future visitors show similar periodic behaviors, that pattern would strongly suggest we're seeing a common characteristic, possibly indicating a formation process or structural property that we simply haven't encountered with solar system objects because they form under different conditions. But if 3I Atlas remains unique, if the dozens of interstellar objects detected in coming years all behave more like 2I Borisov, chaotic and normal and comet-like without precise periodicities, then we'll know this one is genuinely anomalous, and anomalies demand explanation. You can dismiss one unusual observation as measurement error. Two might be coincidence, but if only 3I Atlas, among many interstellar visitors, shows these characteristics, that isolation becomes its own form of evidence, suggesting this particular object differs fundamentally from the general population in ways that require understanding. The engineering hypothesis gains or loses credibility based on population statistics. If artificial probes exist and regularly traverse interstellar space, we might expect to detect them with frequency proportional to how common such technology is relative to natural objects. If 1 in 100 interstellar visitors is artificial, then among the first few we detect, finding one that shows possible technological signatures wouldn't be unreasonable. But if hundreds of visitors all appear natural except for one outlier, that either means artificial probes are extraordinarily rare. Perhaps only this one has passed through in human observation history, or the outlier's anomalies have natural explanations we haven't discovered yet. This statistical reasoning highlights why institutional caution might be justified. Declaring 3I/Atlas artificial, based on current evidence, would be premature, potentially embarrassing if future observations reveal natural mechanisms to had explained the periodic behavior. But completely dismissing the possibility, refusing to seriously investigate it as a hypothesis, would be equally problematic if the object genuinely represents first contact with technology from beyond Earth. Walking this tightrope requires extraordinary care, presenting observations honestly while acknowledging multiple interpretations, advancing research programs that could distinguish between possibilities without prematurely collapsing uncertainty into false certainty. The SETI community, perpetually optimistic about finding signs of extraterrestrial intelligence while perpetually disappointed by false alarms, has watched 3I Atlas with particular interest. Breakthrough. Listen, the most comprehensive search for technological signatures ever undertaken, has pointed radio telescopes toward the comet, searching for transmissions. So far, nothing. No narrow-band signals, no modulated carriers, no obvious broadcasts that would conclusively indicate artificial origin. But silence doesn't prove absence. A probe designed for passive observation rather than active communication might generate no detectable radio emissions. Or it might communicate using methods we haven't considered, optical lasers or neutrino beams or quantum entanglement techniques that lie beyond current detection capabilities. Avi Loeb, Harvard astrophysicist and perpetual advocate for taking artificial hypotheses seriously, has been among the most vocal proponents of considering 3I Atlas as potentially technological. His arguments echo those he made about Oumuamua, that science should follow evidence wherever it leads, even if that destination makes us uncomfortable. The periodic behavior, the harmonic relationships, the chemical anomalies, all stack up into a pattern that natural explanations struggle to accommodate without invoking multiple special conditions that themselves seem improbable. Occam's razor, properly applied, sometimes favors artificial explanations if they're simpler than the accumulation of coincidences required to preserve natural scenarios. But Loeb's advocacy also demonstrates the professional risks of pushing artificial hypotheses too aggressively. His Oumuamua suggestions, while carefully caveated in technical papers, were widely interpreted as claiming definitive evidence of alien technology. The backlash was swift and harsh, with colleagues publishing papers specifically refuting his interpretations, media coverage often framing him as either visionary or crank, depending on editorial perspective. That experience might make other scientists hesitant to voice similar thoughts about 3I Atlas, even if their analysis leads toward conclusions they find difficult to dismiss. Professional reputation, funding prospects, peer respect, all suffer when you're perceived as having abandoned scientific rigor in favor of sensationalism. This social dynamic within science creates systematic bias against considering artificial hypotheses, even when evidence might warrant it. The personal and professional costs of being wrong about artificial claims vastly exceed the costs of being wrong about natural claims. If you propose a natural mechanism that later proves incorrect, that's just normal science, hypotheses tested and refined through observation and debate. But if you suggest artificial origin and later discover you were wrong, you risk being remembered as the scientist who embarrassed the field, who let wishful thinking override careful analysis, who damaged public trust in scientific credibility. These asymmetric consequences naturally push researchers toward conservative interpretations, toward exhausting every possible natural explanation before even considering alternatives. Yet this conservatism has its own costs. If artificial probes do exist, and occasionally pass through our solar system. This reluctance to consider them seriously means we might miss opportunities to recognize them, to study them intensively while they're accessible, to learn whatever lessons they might teach about technologies and civilizations beyond our current understanding. The balance between avoiding false positives and avoiding false negatives is delicate, and different scientists locate that balance at different points along the spectrum, from extreme skepticism to extreme openness. 3I Atlas is testing where that balance should lie, forcing the astronomical community to examine whether current epistemic standards are appropriate, or whether we need frameworks better suited to evaluating claims that sit at the boundary between known and unknown, natural and artificial, ordinary and extraordinary. The polarimetry data deserves deeper attention because it reveals properties of 3I Atlas's dust and surface that spectroscopy alone cannot capture. When sunlight reflects off particles in a comet's coma or off the nucleus surface itself, that light becomes polarized, its electromagnetic waves aligned in preferred orientations, determined by the size, shape, and composition of reflecting materials. Every comet shows characteristic polarization curves, patterns of how polarization changes with phase angle, the angle between sun, comet, and observer. These curves have been measured for dozens of solar system comets, establishing baseline expectations for what natural comet dust produces. 3I Atlas exhibits polarization behavior that places it outside these baseline expectations. Specifically, it shows deep negative polarization branches, meaning at certain phase angles, the reflected light is polarized opposite to the typical direction. This signature appears only rarely in solar system objects associated with either unusually large dust particles, exotic surface compositions, or geometric structures that create coherent scattering rather than the diffuse scattering typical of irregular dust. The depth of the negative polarization branch, the sharpness of its minimum, both suggest something about this comet's light-scattering properties differs fundamentally from what we observe in ordinary comets. Natural explanations exist. Perhaps the dust grains are coated with organic materials that modify optical properties. Perhaps the grains are aggregates with fractal structures that scatter light differently than solid particles. Perhaps the coma contains a population of very large particles, essentially pebbles rather than dust, that create unusual polarization through geometric optics rather than the wavelength scale scattering that dominates with smaller particles. Each explanation is possible, though each requires specific conditions that aren't common in solar system comets, suggesting either 3I Atlas formed under very different circumstances, or its journey through interstellar space modified its properties in ways local comets don't experience. The alternative explanation, that polarization anomalies indicate structured surfaces rather than random dust, gains plausibility when combined with the periodic brightness variations. If the object has panels or facets that reflect light coherently, you'd expect both unusual polarization signatures and brightness pulses, as these structured surfaces rotate into and out of favorable reflection geometries. Metallic or crystalline surfaces, smooth and regular rather than rough and chaotic, produce polarization patterns unlike those from dusty comets. Without close-up imaging that could directly resolve surface features, we cannot distinguish definitively between exotic dust and structured surfaces. But the combination of polarization anomalies with other unusual behaviors creates a pattern where each individual oddity might be natural, but their coincidence becomes increasingly difficult to attribute to chance alone. The coma morphology, its overall shape and structure, provides additional clues about what processes drive 3I Atlas's activity. Most active comets show jets, bright streaks in the coma, indicating where material is being ejected forcefully from specific regions on the nucleus. These jets result from localized outgassing, where active regions breach the surface and vent material into space, while surrounding areas remain relatively dormant. Jets are asymmetric by nature, pointing in whatever direction the active region happens to face when it rotates into sunlight. Their presence creates complex coma structures, fans and spirals that evolve as the nucleus rotates, and different jets become active or inactive. 3I Atlas shows a surprisingly uniform coma, without dramatic jet structures visible in high-resolution ground-based images. The material appears to be released relatively evenly across the visible hemisphere, rather than concentrated in discrete active regions. This uniformity could indicate either that many small active regions are distributed across the surface, their individual contributions blending into an apparently smooth overall distribution, or that outgassing occurs through a porous surface rather than through localized vents, allowing material to seep out broadly rather than erupting from specific points. Either scenario is possible naturally, but both represent less common configurations than the discrete jet model typical of most well-studied comets. The porous surface explanation requires the nucleus to have permeability throughout its structure, rather than being a solid block with occasional cracks. The distributed vents explanation requires either remarkably uniform composition across the surface or some process that maintains active regions in patterns more regular than random geology typically produces. Neither explanation is impossible, but both add to the accumulation of special conditions we must invoke to keep the natural interpretation viable. Color measurements of the coma show variations that correlate with the brightness cycles. When 3I Atlas brightens, it becomes slightly bluer, When it dims, it reddens slightly. This color variation could indicate that different surface regions have different compositions, with icier, more reflective areas appearing bluer and dustier, darker areas appearing redder. As the object rotates, we see different mixtures of these regions, producing correlated brightness and color changes. But the tightness of the correlation, the consistency with which color tracks brightness through multiple rotation cycles, suggests either remarkably uniform distribution of compositional variations or some mechanism that couples color and brightness more directly than simple rotation of heterogeneous surfaces would explain. Spectroscopic monitoring reveals temporal variations in emission line strengths that don't quite align as expected. Different molecules in the coma show brightness peaks at slightly different phases of the rotation cycle. Water vapor peaks at one rotational phase, cyanide at another slightly offset phase, carbon dioxide at yet another. In natural comets driven by solar heating, you'd expect these molecules to be somewhat correlated since they're all responding to the same heating patterns as different surface regions rotate into sunlight. The phase offsets could indicate very specific compositional zonation on the surface, with water-rich regions distinct from carbon-rich regions distinct from organic-rich regions, all arrayed in patterns precise enough to create the observed temporal separations in emission peaks. Or the phase offsets could indicate multiple independent processes operating simultaneously. Perhaps some outgassing is thermally driven, responding to solar heating as expected, but perhaps other outgassing is driven by different mechanisms, internal heat sources, or deliberate venting that occurs on schedules unrelated to solar illumination. This multi-process explanation seems contrived when stated explicitly, requiring coincidental superposition of natural and artificial drivers. Yet it might fit the observations better than single process models that struggle to explain why different molecules peak at different rotational phases with such regularity. The dust production rate, estimated from coma brightness and models of how particles scatter sunlight, appears lower than expected for a comet producing this much gas. Typical comets have dust-to-gas ratios around unity, meaning they release roughly equal masses of dust and gas. 3I Atlas shows gas production substantial enough to create a visible coma, but dust production that seems subdued relative to the gas. This could mean the nucleus has less dust mixed into its ice, perhaps because it formed in a cleaner environment, or because dust has been preferentially removed by previous close stellar approaches we have no record of. Or it could mean the dust particles are larger than typical, heavier and harder to lift off the surface, remaining close to the nucleus rather than dispersing through the coma. Large dust particles are interesting because they're harder to produce naturally through the gentle accretion processes that form comets. Collisions between larger bodies can create debris, but that debris typically includes a range of sizes, from fine dust to large fragments. Finding a comet that selectively produces large particles requires either special geology that generates large pieces preferentially, or mechanisms that filter out smaller particles, keeping them bound to the surface while allowing larger pieces to escape. Neither process is well understood or commonly observed, making the apparent dust-size anomaly another entry in the growing list of features that place 3II Atlas outside typical comet behavior. So rest now with these details settling into your consciousness. Fragments of a larger puzzle we're still assembling. Each observation reveals new peculiarities that might be natural under special conditions, or might indicate something more fundamental about this object's nature. The data accumulates slowly, resolution increasing as more telescopes contribute, patterns emerging as observation campaigns extend across weeks and months. We're watching the mystery unfold in real time, witnessing science at its most fascinating moment, when the evidence is substantial enough to demand attention, but ambiguous enough that conclusions remain uncertain, contested, dependent on assumptions and interpretations that different researchers evaluate differently. This is how paradigms shift, if they shift at all, gradually, through accumulated anomalies that eventually overwhelm the frameworks built to explain them. The artificial intelligence misinformation incident deserves careful examination because it illustrates how easily excitement can override verification in the modern information landscape. In late September 2025, a science communicator named Thiago posted a live stream discussing supposed energy bursts detected from 3I Atlas. According to his presentation, advanced AI analysis of telescope data had revealed periodic emissions of radiation that couldn't be explained through natural processes. The video spread rapidly across social media platforms, accumulating hundreds of thousands of views within days, sparking animated discussions about whether humanity was witnessing its first confirmed artificial interstellar probe. The problem was fundamental. The bursts didn't exist. The AI system employed to analyze the data had either misinterpreted noise as signal, confused terrestrial interference with comet emissions, or suffered from training biases that made it see patterns where none were present. When other researchers attempted to replicate the findings using identical data sets, they found nothing. No bursts, no periodic emissions, no evidence supporting the dramatic claims. To Thiago's credit, he deleted the video upon recognizing the error and issued a public retraction explaining what went wrong, acknowledging the importance of peer review before publicizing extraordinary claims, and apologizing for contributing to misinformation cycles. This incident highlights both the promise and peril of artificial intelligence in astronomical research. Machine learning algorithms can process vast data sets far faster than human researchers, identifying subtle patterns that might take years to discover through traditional analysis. AI has made genuine contributions to astronomy, classifying galaxies, detecting exoplanets, finding optical counterparts to gravitational wave events. But AI systems are also prone to specific types of errors, particularly when confronted with edge cases or novel situations outside their training distributions. They learn patterns from existing data and apply those patterns to new observations, which works well when the new observations resemble training examples, but fails spectacularly when encountering genuinely unprecedented phenomena. The asymmetry in consequences matters deeply. A false positive claiming detection of something that isn't there can spread globally before verification catches up, potentially damaging public trust in scientific announcements. A false negative failing to detect something genuinely present might delay discovery but doesn't typically create the same reputational damage. This asymmetry biases AI systems and the humans who deploy them toward caution, toward setting detection thresholds high enough that false positives become rare, even at the cost of missing some genuine signals. But that caution has its own risks. If 3i Atlas genuinely shows unusual features that current AI systems aren't trained to recognize, we might miss them entirely, while confidently declaring the object natural and ordinary. The broader pattern of AI-related errors in 2025 astronomy provides sobering context. Multiple high-profile claims have appeared and then collapsed under scrutiny. Supposed room temperature superconductors identified through crystal structure analysis that turned out to be known compounds misidentified by algorithms, exoplanet candidates that were actually instrumental artifacts, gravitational microlensing events that were actually data processing glitches. Each incident reinforced the lesson that AI cannot replace human judgment, that algorithms are tools requiring careful oversight rather than oracles delivering unquestionable truth. For 3i Atlas specifically, the AI incident raises questions about how we validate the findings we've discussed. The Lomscargel periodogram analysis used to detect rotational periods is mathematical rather than AI-based, which gives it different error modes. It's less prone to hallucinating patterns that don't exist, but it still requires interpretation, still depends on choices about significance thresholds and sampling corrections that can bias results if applied incorrectly. The fact that the Russian team reported their findings through traditional peer-reviewed channels rather than through AI-discovered anomalies lends credibility, but independent verification remains essential before accepting the periodic behavior as definitively established. Science's self-correcting mechanisms operate through replication and peer review. Multiple research groups examining identical data with different methods and reaching convergent or divergent conclusions. When everyone sees the same signal using different approaches, confidence grows legitimately. When results depend critically on specific analysis, choices, or appear only with certain algorithms, skepticism appropriately increases. 3I Atlas's periodic behavior needs this kind of robust verification. Multiple teams, multiple instruments, multiple analysis pipelines, all independently confirming that the 4-hour positional shifts and 2-hour brightness pulses are real features rather than artifacts of particular observation schedules or data processing techniques. The public's relationship with scientific claims has grown complicated in this era of rapid information flow and frequent retractions. There exists enormous appetite for breakthrough discoveries, for news challenging our cosmic understanding, for evidence suggesting we're not alone. But there's also mounting skepticism, fueled by repeated disappointments, by exciting headlines that transform into footnotes when replication fails, by promises that don't materialize into the revolutionary changes originally advertised. This creates difficult terrain for scientists attempting to communicate ongoing research, trying to convey both the genuine excitement of potential discovery and the inherent uncertainty that accompanies any scientific investigation before conclusions solidify. 3I Atlas occupies precisely this uncomfortable middle ground. The data suggests something unusual occurring, unusual enough to warrant serious study and public interest. But it's not conclusive enough to declare definitively that we've found artificial technology or definitively ruled it out. We exist in science's messy middle phase, where competing interpretations vie for acceptance, where evidence accumulates slowly rather than arriving in revelatory floods, where certainty remains frustratingly elusive despite intensive observation. In this environment, the temptation toward overselling findings grows strong. Professional incentives, funding pressures, media attention, public fascination, all push toward dramatic announcements, toward confidence that evidence doesn't yet support. Resisting this temptation requires discipline that institutions don't always maintain. The careful language of scientific papers, with their hedged conclusions and extensive caveats, doesn't translate well to press releases or news articles or social media posts where nuance compresses into headlines and complexity reduces to simple narratives. The transformation from "we observe periodic variations that natural models struggle to explain fully" to "scientists confirm artificial probe" happens through a game of telephone, where each retelling amplifies certainty while shedding qualifications, until the message that reaches public consciousness bears little resemblance to what researchers actually concluded. Thiago's error and subsequent correction model how this should work when mistakes occur. Acknowledge them publicly, explain what went wrong, remove false information from circulation, accept temporary embarrassment in service of long-term credibility. Not everyone follows this model. Some researchers double down when challenged. Some quietly move on without addressing problems in earlier work. Some maintain positions long after evidence has shifted. But the ideal remains. Science advances through honest error correction, through willingness to admit when you're wrong, and adjust conclusions accordingly. The lesson for understanding 3IE Atlas is that we must maintain skepticism even while exploring exciting possibilities. The periodic behavior might be real, confirmed by multiple independent observations. The chemical anomalies are definitely real, measured repeatedly by different instruments. But interpreting what these observations mean, whether they indicate natural or artificial origins, whether they're unprecedented or simply rare examples of phenomena we haven't studied extensively, that interpretation remains open, contested, requiring more data and more analysis before speaking with confidence. And when that confidence eventually arrives, if it arrives, it will be because multiple independent lines of evidence converge on consistent conclusions, because natural explanations have been systematically tested and found wanting, because the accumulated weight of observation leaves no reasonable alternative to accepting that something genuinely extraordinary has passed through our cosmic neighborhood. The future of 3I Atlas investigation depends on missions and technologies that exist in various stages of planning and development. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents our most tangible near-term hope for studying an interstellar object at close range. Rather than launching toward a predetermined target, Comet Interceptor will position itself at a gravitationally stable Lagrange point and wait. When a suitable target appears, ideally a long-period comet, or better yet an interstellar visitor, the spacecraft will activate, adjust its trajectory, and execute a high-speed flyby, capturing imagery and spectroscopy, impossible from Earth-based observations. This strategy acknowledges the fundamental challenge of interstellar object investigation: unpredictability. We cannot forecast when or where such visitors will appear with enough advance notice to design, build, and launch dedicated missions. By maintaining a spacecraft in ready position, capable of rapid response when opportunities arise, we transform the problem from predict the unpredictable to respond when detection occurs. The approach requires patience. The spacecraft might wait years for an appropriate target, but the scientific return from successfully intercepting an interstellar visitor justifies that patience. A single close flyby would reveal surface features, composition details, structural properties that decades of remote observation cannot access. Comet Interceptor carries multiple instruments designed for rapid flyby science, cameras providing resolution down to meters, spectrometers, analyzing coma composition in real time, dust analyzers measuring particle sizes and velocities, magnetometers detecting any magnetic fields the object might generate. If 3I Atlas were still accessible in 2029, it would be an ideal target, but interstellar objects move too quickly. By launch date, 3I Atlas will be far beyond the inner solar system, too distant and faint for interception. Instead, the mission will await the next visitor, or perhaps settle for studying a long-period solar system comet as backup target, valuable science, even if not the interstellar prize we hope for. Beyond Comet Interceptor, conceptual studies exist for even more aggressive rapid response missions. NASA has explored designs for spacecraft kept in storage on Earth, ready for emergency launch when interesting targets are detected. These concepts employ advanced propulsion, nuclear, thermal, electric, or hybrid systems capable of achieving the velocity changes necessary to catch fast-moving interstellar objects. The engineering challenges are formidable, predicting trajectories with extreme precision, launching at optimal moments with minimal preparation time, carrying enough fuel for major velocity changes while keeping spacecraft mass manageable. But the payoff justifies the complexity. Instead of brief flybys at tens of kilometers per second, optimized intercept missions could potentially match velocities with targets, allowing extended observation periods, perhaps even rendezvous and sample return if the mission architecture supports it. Ground-based observational capabilities continue improving in ways that will revolutionize how we detect and study interstellar visitors. The Vera Rubin Observatory's legacy. Survey of Space and Time, expected to begin full operation soon, will image the entire visible sky every few nights, cataloging everything that moves or changes brightness. LSST's detection rate for interstellar objects is projected at dozens per year once the survey reaches maturity, transforming these visitors from rare curiosities into regular occurrences that we can study statistically. Understanding their population properties, compositional diversity, trajectory distributions. This statistical approach will contextualize 3I Atlas in crucial ways. Is its periodic behavior common among interstellar visitors or unique? Do most show similar chemical anomalies, or does 3I Atlas stand alone? What fraction exhibits brightness variations consistent with precise rotation versus chaotic tumbling? With large sample sizes, we can answer these questions definitively rather than speculating based on 3 examples. If 3I Atlas represents typical interstellar comet behavior, that tells us something profound about how these objects form or survive their journeys. If it's genuinely anomalous among its peers, that anomaly becomes its own form of evidence demanding explanation. The James Webb Space Telescope continues observing comets and other solar system objects when its crowded schedule permits. JWST's infrared sensitivity reveals molecular species and temperature distributions invisible to other instruments. If 3I Atlas remains within JWST's observable range for coming months, follow-up observations could constrain its composition more precisely. Search for exotic molecules that might indicate unusual formation conditions, or, in the most speculative scenario, industrial compounds that wouldn't occur naturally. The spectral fingerprints of manufactured materials differ from natural cosmic chemistry in ways that sensitive instruments can detect, though interpreting those differences requires extreme care to avoid false positives. Radio telescope arrays, particularly facilities like the Very Large Array and eventually the Square Kilometer Array when it becomes operational, offer another investigation avenue. Even if 3I Atlas isn't broadcasting intentionally, it might emit radio waves through natural processes, molecular transitions in the coma, interactions between the comet's plasma environment and solar wind, or conceivably through less common mechanisms we haven't fully catalogued. Sensitive radio observations spanning multiple frequencies could detect emissions that optical telescopes miss entirely, adding another dimension to our understanding of what this object is and how it behaves. The key observational questions for ongoing campaigns focus on several critical areas. First, does the periodicity persist as the comet moves farther from the Sun? Natural rotation rates can change as comets heat or cool, as outgassing patterns shift, as structural modifications occur from thermal stress. If 3I Atlas maintains its 4-hour positional cycle and 2-hour brightness pulse with consistent precision for months or years, that stability becomes increasingly difficult to explain through natural processes, which typically show some evolution over time. Conversely, if the periods begin drifting, if the regularity degrades as the comet retreats from solar heating that would support natural explanations where temporary conditions created apparent precision that couldn't be maintained indefinitely. Second, are there spectroscopic features not yet detected that might provide additional clues? Higher resolution observations with better signal-to-noise ratios might reveal trace molecules or unusual isotope ratios diagnostic of formation conditions, or, provocatively, of artificial composition. Industrial processes leave signatures, specific isotope enrichments that don't occur naturally, molecular species that require synthesis rather than forming spontaneously in cosmic environments, elemental ratios tuned for functional purposes rather than reflecting random cosmic abundances. Detecting such signatures definitively would transform speculation into concrete evidence, though the bar for claiming artificial chemistry is appropriately high, given the stakes involved. Third, can we measure trajectory changes beyond what gravity and natural outgassing predict? Precise astrometry tracking position to milliarc-second accuracy over extended baselines might reveal tiny accelerations consistent with course corrections. This is extraordinarily difficult, requiring years of data and sophisticated modeling to separate genuine trajectory modifications from measurement errors, seasonal effects, gravitational perturbations from solar system bodies. But if achieved, if we could demonstrate that 3I Atlas makes deliberate maneuvers maintaining or adjusting its path in ways that natural processes cannot explain, that would constitute perhaps the strongest evidence possible, short of direct imaging of artificial structures. These questions will be answered gradually as observation campaigns continue and data accumulates. Science rarely delivers dramatic revelations in single moments. More commonly, understanding emerges through patient accumulation of evidence, through gradual refinement of models, through slow convergence toward conclusions that become increasingly difficult to avoid as alternative explanations fail one by one. We're in that process now with 3I Atlas, watching as each new observation either reinforces mystery or resolves it, as the patterns either clarify into something explicable or deepen into something that forces us to expand our categories of what's possible, what's natural, what might be visiting us from the cosmic depths beyond our solar system's boundaries. So sleep now with these questions hovering in your consciousness, knowing that answers approach slowly but inevitably. Tomorrow and the days following will bring new observations, new analyses, new insights that either settle this mystery or deepen it further. The universe is patient. The stars will be there when you wake, continuing their ancient journeys, perhaps carrying with them visitors. We're only now learning to recognize, to study, to understand as something more than ice and rock tumbling through the void. The philosophical dimensions of this investigation extend far beyond technical astronomy into questions humans have pondered since consciousness first turned skyward. What does pattern mean in a universe governed by entropy, by the constant tendency toward disorder? Physical laws themselves are patterns, regularities emerging from fundamental constants and symmetries that govern matter and energy. Planets orbit in ellipses because gravity follows precise mathematical rules. Atoms emit light at specific wavelengths because quantum mechanics dictates allowed energy transitions. Radioactive decay proceeds exponentially because probability operates consistently across vast numbers of identical atoms. These are patterns we recognize as natural, emerging from simple underlying principles without requiring guidance or intention. But some patterns seem to require specific arrangements, configurations unlikely to arise through random processes, even given cosmic timescales. A crystal lattice exhibits beautiful regularity, atoms arranged in precise geometric arrays, yet this order emerges naturally wherever conditions favor crystallization. No designer needed, just physics and chemistry operating according to their inherent rules. A computer chip also exhibits geometric regularity, transistors and connections laid out in intricate patterns. But this order cannot emerge spontaneously. It requires intention, planning, fabrication processes that impose structure from outside, rather than allowing it to self-organize from within. The question facing us with three eyes Atlas is which category of pattern we're observing. Is its precision the precision of crystal formation, natural order arising from simple rules applied consistently? Or is it the precision of integrated circuits, order imposed by intelligence, serving purposes beyond mere physical stability? The data doesn't yet answer this question definitively. We have observations that could support either interpretation depending on assumptions about what natural processes can achieve under exotic conditions we haven't directly studied. This ambiguity isn't failure of science, but recognition of its honest limits, its refusal to claim certainty where evidence permits multiple conclusions. The possibility that we might be observing artificial technology forces confrontation with questions that extend beyond astronomy into philosophy, sociology, theology. If 3I Atlas is a probe, what does that imply about the prevalence of intelligence in the galaxy? About the likelihood of technological civilizations surviving long enough to engage in interstellar exploration? About whether such civilizations typically choose subtle observation over dramatic announcement? Each implication branches into further questions about timescales, about motivations, about whether minds arising under different stars would think thoughts recognizable to us or operate according to logic so alien that communication becomes impossible even if both parties desire it. Citizen science plays increasingly vital roles in modern astronomy, amateur observers contributing observations that professional facilities cannot always provide. For 3I Atlas, enthusiasts worldwide are tracking the comet with backyard telescopes, measuring positions and brightnesses, contributing data to international repositories that help fill gaps in coverage that institutional observatories leave. Geographic distribution means someone is always watching, even when major facilities face weather closures or schedule conflicts. Modern amateur equipment achieves respectable precision, sufficient to detect the periodic variations we've discussed and verify that they're not artifacts of particular telescopes or analysis methods. This distributed observation network serves as hedge against institutional information control, whether that control is deliberate or simply bureaucratic inertia. If professional facilities remain silent or delayed in releasing findings, amateur community can extract what's possible from publicly available data and publicly accessible observation time. It's not equivalent to having Mars orbiter data or JWST spectroscopy, but it's something, a floor below which understanding cannot fall, regardless of what institutions choose to withhold or delay. And, in this case, what amateur observers see corroborates the Russian findings. 3i Atlas does show regular brightness variations, does exhibit behaviors that don't quite match typical comets, does warrant the careful attention and cautious speculation it's receiving. The convergence of professional and amateur observations builds confidence that we're seeing genuine phenomena rather than measurement artifacts or analysis errors. When multiple independent observers using different equipment and methods reach consistent conclusions, when the patterns persist across observation sessions separated by weeks, when the periodicity shows up in data sets processed with different algorithms, skepticism about the pattern's reality becomes harder to maintain. We might still debate what causes the pattern, whether it's natural or artificial, whether it represents exotic physics or familiar processes operating under unusual conditions. But that the pattern exists, that 3i/Atlas genuinely exhibits 4-hour positional cycling and 2-hour brightness pulsing, becomes increasingly difficult to dismiss as illusion. The question then shifts from, is it real, to, what does it mean? And that question, philosophically deeper and scientifically more challenging, is where we currently stand with this enigmatic visitor. It's real. Its behavior is documented. Its chemistry is measured. Its trajectory is tracked. But the interpretation, the framework for understanding what these observations tell us about the object's nature and origin, remains contested. Natural explanations exist, but require accumulating special conditions. Artificial explanations feel cleaner in some ways, but demand we accept extraordinary conclusions that could prove embarrassingly wrong if natural mechanisms eventually emerge that we simply haven't imagined yet. So here we are, at the end of our long night's exploration, no closer to certainty than when we began, but perhaps closer to understanding the right questions to ask. 3i Atlas continues its journey outward from the Sun, following the hyperbolic trajectory that will eventually carry it back into interstellar space, never to return. We have months, perhaps, maybe a year or two, to study it before it fades beyond detection range of even our most powerful instruments. Every observation in that remaining window matters, every spectrum captured, every brightness measurement recorded, contributing to the data set we'll analyze for decades, regardless of whether we ever reach definitive conclusions about what this object truly is. The Russian announcement of periodic shifting wasn't endpoint but beginning, the moment when what had been privately observed became publicly discussed, when institutional silence broke and the broader astronomical community was forced to confront observations that don't fit comfortably into established frameworks. Whether that silence breaks further, whether other agencies release corroborating or contradictory findings, whether the patterns persist or fade as the comet retreats from solar heating, all remains to be seen in coming months. We're watching a story unfold in real time, witnessing science at its most human and uncertain, when the evidence is substantial enough to demand attention but ambiguous enough that honest experts can disagree about interpretation. If 3I/Atlas proves natural, explicable through exotic but understood physics, it will teach us that the universe contains more diversity than our solar system sample prepared us for, that comets from other stellar systems can exhibit behaviors we didn't anticipate because they formed under conditions we haven't directly studied. That lesson has value, expanding our models, preparing us for the flood of interstellar visitors LSST will detect in coming years. But if 3I Atlas proves artificial, if the accumulating evidence eventually overwhelms natural explanations and forces acceptance that we're observing technology from beyond Earth, that lesson transforms everything: our cosmic context, our expectations about intelligence in the universe, our understanding of what's possible when civilizations mature beyond our current technological adolescence. Either outcome changes us. Either answer to the mystery matters profoundly. And the fact that we cannot yet determine which outcome is correct, that we must sit with uncertainty while evidence accumulates and analyses refine, is itself valuable. It teaches patience, humility, respect for the complexity of distinguishing pattern from noise, natural from artificial, ordinary from extraordinary. The universe is under no obligation to make sense on our timelines, to reveal its secrets at speeds matching our curiosity. 3I Atlas will tell us what it is when we've gathered sufficient evidence to hear its message clearly, when our instruments are precise enough and our models sophisticated enough to distinguish between competing explanations that currently both seem plausible. Sleep now. Dream of patterns emerging from chaos, of visitors from distances beyond imagining, of questions that dwarf our current understanding and demand we expand our categories of what's possible. Dream of the moment when uncertainty resolves into knowledge, when ambiguity clarifies into understanding, when we finally know whether we've been watching the most perfectly balanced natural object ever observed, or the first confirmed messenger from intelligence beyond our world. That moment approaches, carried forward by each observation, each analysis, each careful thought given to interpreting what the cosmos has presented for our consideration. And when it arrives, whether we're prepared or not, everything changes. Until then, rest easy knowing that the mystery endures, that questions remain worth asking, that the universe still holds surprises for species patient enough to watch and wonder and wait for answers that arrive in their own time. Good night, traveler. The stars keep watch while you sleep, and somewhere among them, 3I Atlas continues spinning through the void, carrying secrets we're only beginning to glimpse. Thank you for journeying with me through this mystery. If this exploration has resonated with you, if you want to continue following the unfolding story of 3I Atlas and other cosmic mysteries as new discoveries emerge, subscribe to Stay Connected. Share your thoughts in the comments about what you believe we're witnessing, natural wonder, or something more. And share this video with others who look up at night and wonder whether we're truly alone. The cosmos has stories to tell, and together we're learning to listen.